An OTA is an interesting and powerful device, but it's also quite fiddly to use. A whole lot more work than an op-amp, which you can just slap in a circuit and be done. So let's go over the basic steps. First, you select your power supply. You should be using a dual-sided power supply, positive and negative voltage, because we're doing analog signal processing. If you want to use a single voltage, just positive voltage, good luck. It's a bit of a pain. Certainly can be done, but it's pain. So we'll not worry about that right now. Make sure that your positive and negative voltages are the same, for example, plus or minus 7 volts, so that your circuit ground is right in the middle. And of course, the total voltage of your supply is so that you have headroom, so that you have enough power to supply whatever load you need, whatever. You just make sure you have enough power. You know how to do that for your circuit. Now, the actual circuit diagram I use for the OTA just has the relevant portions. It has the differential voltage input, the current input for gain, and the current output. You'll often see it drawn with the linearizing diodes in there. That's just not necessary. We know they're in there, but they don't affect the actual circuit. It's just something you have to do to the chip, just like plugging it in. Your actual OTA, and the LM13700 has 2 of them that share a supply rail, but I'll not worry about that right now. We'll just say that this is one OTA. We've got your V plus and V minus, or VCC and ground for a single-sided supply, but again, that's a pain. So obviously here, you just hook up your negative and positive voltage, and bypass capacitors if you want, all that stuff. So then we have the differential inputs. Let's call that I plus and I minus, I for input. So the first thing you need is the peak-to-peak voltage of your signal. We're going to assume the input signal does not have a DC bias. We're going to assume it's nice and centered on 0. So you'll have your signal, and it'll be centered on 0. So your peak-to-peak is, of course, the biggest to smallest, the most positive to most negative voltage your signal will have. So half of that, if it's symmetrical, if this is 0.5 and minus 0.5, so 1 volt peak to peak, your magnitude is going to be 0.5 volts if peak to peak is 1 volt. So basically, whatever the biggest positive and negative your signal can be, if the highest positive voltage is 0.5 volts and the lowest negative voltage is minus 0.6 volts, then you want 6 here, 0.6 volts. If this goes to 0.5 and this goes to negative 0.6, you want the furthest it goes from 0. The reason for that is because we have to control the differential input voltage. On the op-amp does it for us with feedback, but we are not using feedback. So the differential voltage, the input, has to be very small. So we have to use a voltage divider to take the signal and bring it down to a useful level. Now in the data sheet for your OTA, you will find a graph, and it'll have lines saying with and without diodes, and it's basically your differential input voltage versus your signal distortion. The bigger the differential voltage, the bigger your distortion. So you have to look at that chart and decide, okay, I can deal with 10%, 1%, 0.1% signal distortion at worst. How distorted are you going to let your signal be? Then you look at the line for with diodes and you say, okay, so 0.1% signal distortion using the diodes, I can get the differential voltage to be this big. So for me, I decided my input signal is 1 volt peak to peak, and I decided I'm willing to accept 1% signal distortion. So I looked in my data sheet, and with the diodes, 1% signal distortion, it said 100 millivolts differential input. One input is going to be ground, one input is going to be our signal, so the furthest from 0. So 1 volt peak to peak, 100 millivolts from 0 is actually 200 millivolts peak to peak, because it can go up 100 millivolts, down 100 millivolts. So basically, we want to shrink our signal so it fits. So by a fifth, roughly. So we do that with a voltage divider, and I'll just use a potentiometer. This is just how I set up the circuit. When you actually get the circuit built, I'm sure you'll use regular resistors, but the easy way to configure is, again, trim pots. Trim pots are the world's best thing. So what you can just do is you take a trim pot, and you put positive on one side, ground on the other, and you just measure here. So let's say this was 7 volts, and you want to reduce that to 10%. So let's say you wanted 0.7 volts. So you just hook up your multimeter and turn the potentiometer until you get 0.7 volts, and then this is 2 resistors, so you measure from one end to the wiper and the other end to the wiper, and there's your 2 resistors. You can also just do math. Whichever you prefer. You can do math, you can use a potentiometer, but this is just a nice, quick, easy trick that doesn't involve getting out the calculator. So once you know how much you're going to reduce your signal, then you can actually set up the voltage divider. So you have your input signal, reference to ground. Through a voltage divider, we're treating this signal as a power source. So the voltage divider will be referenced to ground, and this will be your input, your non-inverting input. So just like you'd set up a voltage divider with a power source, we're setting up a voltage divider with the signal. So it's going to divide it down into our non-inverting input, and then relative to 0, it will be great. So remember about input bias current on an op-amp and how I said that you don't necessarily need to worry about it unless you're doing higher quality stuff? That's not true with an OTA. First of all, an OTA has an order of magnitude higher input bias current. For an op-amp, it might be nanoamps. For an OTA, it's probably microamps, according to my datasheet. Also, for various reasons, it is incredibly effective at including error in your circuit. It causes a lot of error. If you ignore it, you're just not going to have any success at all. You have to impedance match because you're bringing this signal down into the millivolt range. And now you're working with microamps. That's only an order of magnitude difference, so it's affecting it a lot. So you're going to have to impedance match, but that's easy. That's nice and easy. We just have a parallel input impedance on this pin because you've got one wire here and it goes out to ground 2 different ways. So if this is R1 and this is R2, then it's just your parallel resistance formula, 1 over R prime equals 1 over R1 plus 1 over R2. So you just divide this resistor into 1, divide this resistor into 1, add them, divide it into 1 again, just flip it reciprocal, and that gives you your other resistor. Or again, use a potentiometer. So I'll show you on my oscilloscope later what you can do, and not a potentiometer really, just a variable resistor. I use a potentiometer because it's a trim pot, but you use a variable resistor from circuit ground into your inverting input. So I'll show you on the oscilloscope how you can just center your signal visually on an oscilloscope and it'll work just fine. You basically impedance match this way. Or you can use a calculator. Using the calculator is still handy because it tells you about the value, but you can roughly approximate. Like if this ends up being 60 k ohms and this ends up being 6 k ohms, then you're going to want like 5 k ohms or so. So put yourself like a 4 k ohm resistor and a 2 k ohm potentiometer and it'll be nice and easy to handle. But you're just using a variable resistor to impedance match this parallel resistance or do the math. And then once you know the value, you can just throw in a regular resistor. So that takes care of the signal input. A voltage divider brings the actual signal down to a reasonable level, and then we impedance match the inverting input that it's measured against. So this is a non-inverting, just a regular amplifier. So then you have your linearizing diodes. I'll just call that D. So here's your linearizing diodes. This doesn't change. You give it a current, and you just give it a current and leave it there, and it makes the circuit more stable. It makes the chip more stable. So once again, this one's easy. You connect positive through a variable resistor right in there, and you just connect your multimeter in current measuring mode. You measure the current, amp meter, and you look on your data sheet and you see that mine says the diode input current should be absolute maximum rating of 2 milliamps. And when I look further in the data sheet, it says 1 milliamp is pretty good. So we say 1 milliamp is pretty good. So you put in your amp meter, and then you adjust your variable resistor until your amp meter is reading 1 milliamp. So then you know what value that resistor should be, and you put it in. Nice and easy. So then you need your IABC, your amplifier bias current. This is the current that controls the gain, the actual input that is important enough for me to draw a line right here. Looking on the data sheet again, it says an absolute maximum rating of 2 milliamps, and keeping your maximum at 1 milliamp is pretty good. So let's aim for 1 milliamp at the high end. So the highest volume will be 1 milliamp, and then going down to 0 milliamps, so between 0 and 1 milliamps will be the volume control, or the gain control more generally. So let's call this IABC. So what is our gain control? You can use a potentiometer, a little knob as a voltage divider. You can use voltage output of some sort of microcontroller connected to a digital to analog converter. Any way you can get a variable voltage. This is called a voltage controlled amplifier. In this configuration, you just put a voltage across a resistor that gives you a current into the gain. Nice and easy. So once again, we have an actual potentiometer this time. I'm going to say this is the volume knob. So you have a volume knob. You've got positive and negative supply across the volume knob. So this is going to give you the full range of voltage to control this current. Then let's put a variable resistor here. You go from the wiper, which is your voltage, across the variable resistor into IABC, and again put your multimeter in current mode here. So what you do is you turn this resistor all the way up, and you turn the potentiometer all the way to the highest voltage. So you want to be all the way up at your positive supply. So that's going to be maximum volume. Maximum volume is here. Minimum volume is here. So put it all the way at maximum volume, and then turn up this variable resistor and measure the current. At maximum volume, you want the bias current here to be 1 milliamp. So the potentiometer is at maximum volume, and you turn this resistor until your amp meter reads 1 milliamp. And then once you get that correct value, you put in the fixed value resistor, and the potentiometer stays because that's your knob. You know, whatever voltage control you have here, the point is that you're getting the correct current in at maximum volume, and then you'll just have less current as you turn the volume down. So far, fairly straightforward. There's one more pin. Obviously, that's out. There's your output. So how does your output work? Remember that the OTA has a current output. It's a constant current source. So what you do is you have a resistor in parallel. So you have a resistor which connects to signal ground. Your output connects into this resistor, and here is your actual out. This is your voltage out. This resistor is going to give you your maximum voltage swing because you have your signal in swing, but you want your signal out swing. The idea is to amplify the signal. You want a higher total voltage. So you have a certain resistance between output and circuit ground. The OTA is going to put out a certain current. What is that current? You have your input differential voltage times your transconductance equals your current output. What is transconductance? Once again, it's just on your data sheet. It's amps per volts. It's units of Siemens, which is amps per volt. So you get input volts, output current. So amps per volts times volts equals amps. Voltage in times transconductance equals current out. Your data sheet is going to have a range, minimum, maximum, typical, whatever. But you'll notice I put a potentiometer or a variable resistor here again, and that's because I just hooked it up to my oscilloscope, and I just turned this variable resistor until I got the amplitude of output signal I need. Just put a sine wave in, and then get your maximum. So you turn your volume all the way up once again. Turn your volume all the way up, and then you measure on your oscilloscope the biggest signal. So if you turn the volume down, it's going to be smaller. So measure at maximum volume how big you want your output signal at maximum volume. That's the value of your resistor here, which you then, once again, swap out once you've measured it into a regular resistor. If you don't have exact values of resistors, if you say you want a 4.9 kilo ohm resistor, well, you probably have a 4.7. But you can put two 1Ks in series. 4.7 plus 1K plus 1K equals 4.9K. Or if you're just making one device, you can just leave the trim pod in and take it back out later when you're done with that device. But that is how it works. Positive and negative input voltage. Your input, non-inverting input, is put through a voltage divider to bring it down to a reasonable level that the OTA can handle according to your data sheet and how much signal distortion you're willing to have. You just impedance match the inverting input with a resistor, which is the parallel resistance here, or just measure it with a trim pot. Your diode input is just a specific fixed current. It never changes, so just figure out what it should be. Half of the maximum rating, half of the absolute maximum rating is probably good. So you just attach your voltage, figure out a resistance, and throw it in there. And I like to use my multimeter in current measuring mode and a trim pot to figure that out, and then you can stick in a fixed resistor later. Your bias current, again, is a voltage divider from positive to negative voltage through a resistor. The resistor controls the current at maximum volume, which is your positive supply rail. Minimum volume is your negative supply rail. So you figure out the resistance to give you the current 1 milliamp or so for mine, IABC at max volume, and then it'll just go down linearly from there. And your output is a current again, and you can guesstimate the transconductance from your datasheet. Input differential voltage times transconductance equals output current, or just use, once again, a trim pot variable resistor at max volume to figure out the maximum voltage swing you want. More resistance is more voltage because V equals I times R. V equals I times R, and the current is the same. For a certain input voltage and a certain input current, the gain, so this is the signal, this is the gain. For a certain value of both of those, you're going to get a certain current out, which is your transconductance, times your input voltage. So if you increase the resistance, but keep the current the same, you increase the voltage. If you keep the current the same and decrease the resistance, you decrease the voltage. So bigger resistor, bigger output voltage swing. Now, my chip includes, the LM13700 includes a Darlington emitter follower buffer on it. I tried to use it, and it's goofy and doesn't work, and I don't know why. But I put it into an op-amp in unity gain amplifier mode, and it works fine. So this part's working. If I put it into an op-amp and buffer the voltage that way, everything works fine. But my chip's onboard buffer, the Darlington emitter follower, is not working the way I expected it to. And it's not working the way the datasheet says it should. And I even confirmed the datasheet's circuit diagram with other diagrams on the internet, and they're the same, so it should work, but it doesn't. So I may have defective chips, I may be doing something wrong, I don't know. But again, you just have your op-amp, and then you have this voltage, this out right here. You just stick it into the non-inverting. You stick your output into the inverting, and there's your buffered out. That's all it is. Signal into non-inverting, output feedback into inverting, and then your output is your signal. That's just your unity gain buffer. And that works fine. I'm sure I will do a follow-up when I figure out how to use the one on the chip properly. But for all I know, my chip is just defective. But in any case, that is the basic operation of the OTA. So let me just show you a couple things on my oscilloscope. So I'm using plus and minus 7 volts for a total of 14 volts peak to peak as my input power. My input signal is the yellow in the middle. It is a 1 kilohertz, 1 volt peak to peak sine wave from the oscilloscope's function generator. The output, this is coming out of the buffer, the unity gain op amp. So I have configured it so I'm getting a total of 6 volts peak to peak from 1 volt peak to peak at maximum volume. So if I turn the volume knob, which is that potentiometer, this is me turning the volume knob. I can turn the volume down and up and down and up, and you can see the amplified signal voltage just goes up and down, and it does it very nice and smoothly. This is because I have kept it within the range of my datasheet's 1% signal distortion. If I had huge voltages here, it wouldn't be linear, it would be, I don't know, exponential, logarithmic, something. But because I have correctly limited my signal input voltage with the voltage divider, we get a nice, smooth, linear voltage gain up and down. So first, let me show you the effect of changing the input impedance on the inverting input, where I've just got ground connected through a variable resistor. So I'm just going to change the resistance on the inverting input that's only connected to circuit ground. If I change that, you can see very violently, I'm changing this by less than a kilo ohm at a time. Look at that. So I've got a 4.7K fixed resistor and a 2K trim pot. The trim pot is only got a swing of 2K ohms. And if I turn it down all the way one way, the signal is long off the screen and the other way. Like right now, I'm barely wiggling. I am breathing on this trim pot, and you can see it wiggling by that much. So it is incredibly sensitive to input impedance matching, unlike the op amp where the error is well and truly manageable. Now, if I turn the gain down all the way, so now it's a horizontal line, so now it's at minimum volume and it's basically just a line. Let me change the input impedance now. You see, nothing's apparently happening. It is, of course. And if I increase the zoom, you've got an incredibly noisy signal, and if I change it now, hopefully, you can see it going, no, it's completely lost within the noise. Completely lost within the noise. Let me bring that back down. And then if I turn the volume, let's say halfway. So put the volume at halfway, and now you see that as I change the volume from 0 to this, there is a DC bias being added to the signal by the mismatched impedance on the two inputs. And that DC bias is being amplified. In this case, it's down. If I change the bias to be above instead of below, by changing the impedance on the inverting input, then I change the volume and you can see a positive DC bias is being amplified. So turn your volume all the way to maximum, then you can impedance match by changing the resistance on your inverting input, get it looking nice and centered, and now when I change the voltage that controls the volume, it's nice and centered again. So if you're using my method of trim pots and an oscilloscope, that's how you do it. Make sure you do everything at maximum volume to center it. Otherwise, do some math and then test. And if all else fails, you can always, pass it through a series capacitor into another buffer and remove any DC bias that way. But doing it this way, make sure you get your full headroom for amplification. Because if there's a DC bias you have to remove later, that means that you've lost some headroom for amplification. That depends on your circuit whether that's a problem. So the other thing I'll show you is the resistor on the output. Remember, you've got the output pin to a resistor in parallel, and then I plug that into my buffer, and I said that the size of that resistor controls the maximum voltage swing. So right now, if I change my volume, we're going from 0 to about 6 volts peak to peak. If I then change the resistor on the output, I will reduce it. So I'm making the resistor smaller. So now we're at about 4 volts peak to peak. And then I do my volume all the way up and down, and we go from 0 to 4 to 0 to 4. And then if I go down to this resistor and turn it up instead, I can get all the way up there, and of course I can start to clip, but I have 14 volts on my supply, so 8 volts peak to peak is not going to be a problem. So now we're at 8 volts peak to peak, and I turn my volume knob. I haven't done anything else to the circuit. Turn my volume knob up and down, and now we have an 8 volts peak to peak output swing. So I can change my at maximum volume. This is at maximum volume, so I turn my output parallel resistor down until I get the 6 volts peak to peak swing I want. And now if I change the volume knob, I get the correct maximum voltage swing. And then you just power amplify this and put it across your speaker. And that's the output voltage that you want to put across. So you have your peak to peak output voltage, and then you have the impedance of your speaker determines the watts that go across it. That sort of thing. But that is an OTA in simple voltage amplification mode. It's definitely a contributing factor as to why people do not use OTAs anywhere near as much as they use op amps. There's just more to do. But I was introduced to OTAs by a group of people interested in analog audio who got into my 555 timer video and shared it on their group. Hello! And I can tell you that I have seen the power of the OTA now, and how incredibly easily it lets you do some analog audio things that op amps just don't let you do without a whole lot more complicated circuitry. And you absolutely can do it other ways, and nowadays, again, a lot of this processing would just be done in software. But if you're doing it in an analog fashion with chips, the OTA is going to make your life so easy as long as you get down these basic configuration steps. So, as usual, if my explanation was bad or not enough, please let me know. I can always change this video or do another one. Until then, I'll be seeing you.